Okay. Okay, so yeah, today I will be presenting our recent accepted research paper for ITSC 2020. This is a collaboration between Arthur and Simona and myself. And the paper is about traffic accident risk forecasting using contextual vision transformers. So we'll start first by some motivation about the problem that we were trying to solve or tackle in this paper. So the motivation for us was that the number of traffic accidents that happens globally are quite significant, and it has a lot of impact on the economical and social and health and social population all over the world. Just one simple number that was reported by the NESTA in US, that more than 5 million traffic accidents are happening every year in US. And even the World Health Organization has reported that more than 1.35 million fatalities are happening worldwide as a result of traffic accidents happen. So the impact of this problem is quite huge. And there has been a couple of works or a number of works in the literature that try to use computational based method to try to tackle this problem. So usually in the literature, this traffic accident risk forecasting is commonly formulated as a time series forecasting task or time series prediction task. So in this kind of formulation, you have like the historical kind of traffic accident for a specific city or region or bounded by some kind of latitude and longitude. And there could be some other additional information other than the historical traffic accidents records. Could be some contextual information around these accidents. And the idea or the task in this kind of formulation is to predict the future traffic accident risk. So for instance, if you have a historical traffic accident data from past 4 weeks or past 3 hours, the idea is to predict the traffic accident risk in the future. This future could be the next hour, next 2 hours, or next day. But usually this kind of most of the work are focused on the short-term kind of prediction within hours. Because as we will be discussing through the presentation, there are a lot of kind of attributes that can affect the prediction for this. So longer-term predictions at the moment are not still on par with short-term prediction ones. So the short-term prediction ones are more promising. So in this work, we are also following the same kind of short-term prediction for the accident risk. And by default or by nature, this kind of problem is often tackled using two different types of models or data-driven models. Because this is a spatio-temporal problem, so we are trying to geolocate a specific area that happens with this kind of accident happens. You have this kind of spatial kind of requirement or constraint, and also you have a temporal. You have some historical data, or you're trying also to predict in the future. So you have these two aspects. So usually in the literature, the previous works have been tackling this using two different types of models. One for that focus on the spatial, and one will focus on the temporal, and they might have another model or another technique to fuse this kind of the outputs from these two models together. In this work, however, we are formulating a new kind of formulation for the problem, and we tackle the problem using a single one unified model that can account for this spatio-temporal nature, and also it can accommodate additional information such as the contextual information around the accidents. So before we get into the actual proposed methodology here, we will just go through some of the main definition that will be our assumption that we have been doing in this kind of research, and that has been already been commonly done in the literature. So usually the idea for in order to limit or modulize the traffic accident risk prediction, the researchers try to confine a specific area and try to test or train their models on. So in order to do so in an easier way, they tend to represent the geographical location in a grid city representation. So let's say that this is like the city center and around the New York City, and defined by a certain latitude and longitude. And the idea is to divide this area by equally sized cells, frozen columns, and the task would be at this is to predict the accident risk prediction for each kind of separate cells. So this makes a problem more kind of modular in a way, or more in a digestive way for the current models or data-driven models specifically. So this kind of assumption might not be the best solution out there, because you will squeeze or some kind of geographical information might be missing in this representation. But this is currently the common way for representation city when it comes to traffic accident risk prediction. And of course, these cells are equally sized. So this is the first kind of definition or the assumption that we have. Also, when we talk about traffic accident risk, what it could means a lot of things for different people. But in this kind of paper, the traffic accident risk definition that we have, that given this grid city representation, that the traffic accident risk is defined as the summation of the different types of traffic accident that happens at this grid cells. So what are the types of traffic accidents that we have here? So based on the kind of notion in the literature, they usually categorize the traffic accident to the three discrete types of accidents, namely injured accident, fatal accidents, and minor accident. So minor accident is like near misses, or could be some kind of some accident that does not involve any injuries or any fatalities. So this is the lowest or lowest risk here, the lower one in terms of the risk accidents. The other one is the injured one. It has involved some injury as part of the accidents. The higher risk one, which is the fatality, which if someone is died as a result of this accident. So each one of these types has a certain value. So this value is just a simple 1, 2, 3. So if it's a minor accident, this value gets 1. If it's an injured accident, will be 2. Fatal will be 3. And here the accident risk, if we can give an example for, if let's assume in this specific grid cell here, if there has been 4 minor accidents and 6 injured accidents. So the accident risk in this case would be, it will be 4 multiplied by the type of the accident, which is 1 in this case, because we have 4 minor, so it will be 4, plus the injured accident, we said it's 2, for instance, two injured accidents, so 2 by 2 is 4, so the total of this kind of risk for accident will be 8. So this is a summation of the types of the accident that happens at this kind of location or cell here at a specific time. So this kind of the outlay for the problem formulation that we will present here. So our formulation is quite, in this paper, is quite different from the normal kind of formulation that has been done previously in the literature. So we have a new formulation here, rather than the time series forecasting task. We reformulated into an image regression task. So instead of having like a time series data, like a tabular format, we reconstruct this information in an image kind of based formulation or representation, that we can be feeding it to image-based deep neural networks in order to get some kind of predictions. So the formulation is as follows. So given the historical observation of a traffic risk that we have described previously, so imagine we have for this kind of matrix, each cell we have the risk values for it. So this representation can be sort of as an image. But since we are dealing with historical data, so a one single image of this represent the traffic accident risk at one time. This one time could be during this current 1 hour or previous 1 hour. So since we as we mentioned, the historical data plays a great role in the modeling or the forecasting for the traffic accidents, we will have a multiple of these ones. So it's not be just one rectangle like this. It will be multiple of them, which correspond to the time. So this is the kind of the formulation that we have, and here we will discuss in more details what are actually the proposed framework that we have. So our proposed framework is called CVIT, which refers to or abbreviation for context visual transformer. So this kind of visual transformer architecture is one of the kind of successful currently in a number of tasks when it comes to image-based tasks in the literature, and has been achieving really superior results in a number of benchmarks. So our framework is inspired by this architecture, but the inputs or the inputs and the information that we feed into this architecture is quite different from the normal kind of formulation for the visual transformer networks. Specifically here, our CVIT architecture, it consists from three main components. The first one is the historical risk map encoding stage, this one at the bottom, and the encoder stage, which this one, bounded by the rectangle here. And the third one is the contextual information encoding, which is this one here. So are the main three parts of our model. We'll start first by this historical risk map encoding at the very bottom in this figure, as you can see here in a more details. So the idea of the risk map encoding is to how to represent the risk map. As we said, it will be represented as an image in a way that the transformer encoder, which is part of the main part of the visual transformers, can digest it easily. So usually the transformer or visual transformer works on a sequence of tokens. So if we have this kind of image, we segment it equally to an ordered sub segments of the image, and we fed it to the transformer encoder as a sequence of patches. That's why we have here, it's called patch embedding. So this kind of sequence of sub images called patches. So the idea of having this kind of patches is similar to the concept of divide and conquer. So you have a huge image. This kind of resolution of image will be representing the spatial resolution of the area that you are trying to predict the accident risk for it. So let's assume you are trying to predict a city-wide traffic accident prediction or a state-wide kind of risk accident prediction. So this kind of formulation help us to scale to whatever the size of the region of the city or a region or a state or even like a national level, which makes one of the advantages of this kind of formulation, because if we are formulating as a normal or a typical time series forecasting, this kind of dimensionality will be really huge, and it will need further pre-processing stages in order to reduce the dimensionality if we are trying to predict like a huge or a large area of a city, trying to predict the accident risk for it. So this kind of formulation makes it more easier and more scalable to whatever the number we can. The size of this image could be configurable, could be any size of it, but at the end of the day, it will be subsegmented into batches, small batches that will be fed into our model. So another rationale or a kind of motivation for this, as we said, this problem has a spatial and temporal aspect to it. So usually some of the assumptions that if some geographical locations which are closer to each other, they might be affecting or have some kind of correlation when it comes to accidents. So for instance, if accident happens in some areas, or traffic is being congested in some area, this might affecting other areas as well, or the potential of having the risk of having accident in other areas could be there. There could be some correlation there that might not be quite visible just by eye, but could be based on the historical data set. This could be a prominent trend in it. So this kind of formulation also makes it easier to capture this kind of correlation easily. So after we segmented in the image patches, we fed all the sequence of patches or sequence tokens of patches into an embedding layer or an embedding information. So embedding layer is more of a kind of, you can think of it as a learnable lookup table. So you fed all the kind of image sequence patches that you have into the embedding layer, and the embedding layer tried to represent these patches in a more compact representation that can be easier to be learned during the inference time, during the training and also the inference. So this is the part that's more concerned about the historical map, risk map encoding. The second part, which is here, the transformer encoder, this is essentially the main, similar to the traditional vision transformer, which is consisting of the main component is the self-attention mechanism layer and a number of feed-forward layers within it. So the self-attention makes the encoder focus more on the areas in the input that has more valuable information. For instance, here, if we can see this a risk map for a specific region over the past 7 days, for instance, we can see there is some hot areas. This means that it has higher risk of accidents, and there is, for instance, on the boundaries, there are less number of accidents, or could be zero accident. So this kind of self-attention mechanism makes our model more efficient on where it actually tries to model the areas in the input maps of the risk, of the traffic accident risk. So instead of like bluntly digest or process all the different areas in the input, the self-attention helps the model to focus on areas that might have more valuable information. This is in a more kind of a simple way to illustrate it, just without going into too much of the details here. The output from the encoders are fed into or fused together with the contextual embedding layer, which is the third component of our model, where, as we mentioned, the other contextual information around the traffic accident might influence the model, or the predictability, or the output prediction out of the model. So this contextual information, such as the time of the day that accident happened, whether this day is a holiday or not, the weather condition in this day of the accident, or this hour of the accident, could be cloudy, sunny, rainy, also the temperature as well. And other information could be the traffic flow within this area or cell in the map of the risk map. So all this kind of contextual information are useful when you're trying to do a prediction about the risk of an accident. And this all information are fed through a contextual embedding, similar to linear patch embedding, but this works on more of like textual information or more of discrete information that represent this kind of contextual information. So it's just a linear kind of embedding layer that try to compact the representation of all this contextual information in a way that could be easier to be learned through the framework. So this contextual information and the output from the encoder that are fused together, and they are passed through a fully connected layer just to predict the accident risk map over the next T+1. So T+1 could be, as I mentioned before, it could be the next hour, next day, but in our case here, it's a next hour. So we rely, our historical map is that we get the risk for the previous 3 hours. So over the past 3, if let's imagine we are at a time T, so T-3, which here it's 3 hours before this time, we get the information of the accident that happened during this previous time. And we try to predict the next hour, what's gonna be the traffic accident risk. But in addition to the past 3 hours, we also accommodate the past 4 weeks for this specific region, what was also the traffic accident risk. So the historical accident risk map for us, it at this stage became 7, which is correspond to 3 hours, and 4 separate weeks, previous weeks, for this specific area. So this makes our historical map image, you can think of it as a multi-channel image, where the channel of this image is the number of historical data, which is in our case is 7. So you can think of it as an image with 7 channels that correspond to the historical data, and the spatial resolution is the resolution of this kind of city area that we are focusing on. And the output of our model here is the same kind of city, the risk for this specific region, but over the next hour. I hope this is more clear for what are the inputs and what are the outputs. In order to train and evaluate the performance of our model, we utilize 2 publicly available traffic accident datasets, the New York City accident record dataset and the Chicago dataset. These 2 datasets are quite similar to each other. So they have reports of accidents in the New York City. It was the range of the reporting accident was from January 2013 to the end of 2013. And for the Chicago, it was from February 2016 to September 2016. Both 2 datasets has accident records, and New York City, since it's more larger, it has more records of accidents, 147K, Chicago's 44K. The two accident dataset also has taxi trips. So taxi trips are this is data was collected from the taxi within these cities. It has information about the location of the pickup and drop off of the taxi trips, and also the places, latitude and longitude of these trips. The value of this kind of trips is to, based on it, the designers or the organizer of these data sets were able to get information of the inflow and outflow information about the traffic for each, based on the different grid areas within the city. The 2 data sets had weather data, such as the temperature, the condition of whether it's sunny or rainy, and so on. And also the road networks information about the area was included in the 2 data sets. And New York City has more additional information that not present in Chicago, which is BOI's point of interest. So in New York City, including the all reported accident, they also has some semantic information about the geographical location. So instead of just putting the latitude and longitude or the boundaries of each grid cell, we have also included some information about whether this area is like a residential area, or it's a school zone, or it's a shopping center area, or something, some semantic information about each geographical location. So this is only available in the New York City dataset. So we trained our model using these two data sets. So we trained one model for the New York City and one model for the Chicago data set. And the organizers of this two data sets have splitted each data set into 3 different splits: training and testing and validation. So they had roughly I believe it was 80% for training, and no, it was 60% training, 20 validation, and 20 for testing. This is for the 2 data sets. And of course, the splitting was done like respecting the kind of the temporal information, so that they make sure there's no kind of overlapping between the times, the reported times of the accidents are included in the different splits. So giving this kind of splitting, we trained our proposed framework, the Context Vision Transformer, and this was the kind of the evaluation for the results based on these experiments. So we reported according to 3 different evaluation metrics, namely root mean square error, and recall, and map, which is mean average precision error. So RMSE, so is some kind of, you can think of a metric that measure how close or far away our prediction are from the ground truth traffic accident risk value for this specific region. Recall is more about the accuracy, how accurate our model is able to give prediction in the different scenarios. And maybe or map is mean average precision. So it's a ratio between how many times our model was able to provide good result versus the number that our model was giving false negatives, or things that think it's an accident but it's not actually an accident. So this is kind of a ratio for it. So the trend for its RMSE, so the lower the number of RMSE, that's mean the better this solution is. The higher the recall value, the more better this model is. The higher the mean average precision score is, the better the model is. And we have our model here, reported result for it, and we compared it against 6 different baseline models from the literature that has been also tested on these 2 data sets. Most of this, as we mentioned before, as this is a spatio-temporal data nature of the data set or the problem, all of these kind of solution, the internally has 2 different types of models. So the main component for it, which is for the temporal modeling, is based on recurrent neural networks, or this recurrent neural networks has different kind of variants of architecture. They have GRU, or gated recurrent units, or LSTMs. So GRU is this one, RNGRU, they are using recurrent neural networks. This one, as I believe, also it's a more encoder-decoder architecture, but it's also using recurrent neural networks and graphical, I think graph neural networks as well. Here they are using a hybrid architecture between recurrent neural networks, which is LSTM, and the convolutional neural networks. So convolution for the spatial kind of modeling, and LSTM for the recurrence or the temporal aspect. GCN, also they are using graphical convolutional neural networks with RNN. GSNet, which is, this is currently the state-of-the-art architecture or model on those 2 data sets. And as you can see from this kind of results, we have outperformed GSNet, which is, to the best of our knowledge, currently is the best performing one, was the best performing one before us. So we were able to outperform them quite reasonably in a number of the on the two data sets, and with in some cases huge number here, like in the Chicago data set. In the New York City, we managed to have a comparable or slightly better performance than them, but the more major kind of performance boost was in the Chicago data set. This kind of reporting with on the whole testing split of the two data sets during all times. Here, this is a sub kind of sub times. We only tested on times in the data set that has high frequency times of accidents. This typically times during the rush hours, so from 7 a.m. to 9 a.m. and also during time from like 4 to 7 p.m. from 4 p.m. to 7 p.m. So this is a common practice in the literature to report the total kind of during all the times, and the another reporting during the time that has a huge amount of or number of frequency of accident happening. Our model continued to be performing better than the state-of-the-art GSNet, and of course the other baselines as well. So again, same trend, better, much better in Chicago, slightly better in New York City. But the more kind of more added value for our proposed framework in comparison to the state-of-the-art GSNet is this figure as well. So this figure represents the number of parameters required by our model, CVIT and GSNet, in order for the training, the model, the number of parameters need to be optimized during the training. As you can see, that the GSNet requires a huge number of parameters, more than 6 million parameters to be optimized, while our CVIT model only requires 0.27 million parameters. So this is a huge difference, and it makes the deployment of our model more easier in case in real life scenarios, because this will impact the real-time performance of the model as opposed to the GSNet, which requires a quiet number. So in combination between the result that we have and also the real-time performance and the number of parameters, we can see that our model has achieved a quite resilient results, and was more than competitive than the state-of-the-art and the other baseline as well. So that's it for my presentation today. I hope everything everything was clear, not very vague, and I am ready to if you have any question that you would like to ask.
Hi, I've got a question about the data splitting. So you mentioned that you wanted to, was it splitting from, if it's 60, 20, 20, would it be splitting on the first 60% of the year, say from January to July, and then the other split would be according to that?
Yeah, so at different times, it will based on, like, for instance, let's just go back to this reporting. Here, so for instance, this is like 12
Thank
months.
you for your presentation.
Thank you, Toto. I think you have internet problem too. So, so in this case, we have 12 months. So we split based on this 12 months. So we'll have, for instance, first 4 months, not 4 months, first 8 months, for instance, for training.
Yep.
And the rest, last 4 months, 2 and 2, 1 for training, 1 for validation, 1 for testing.
Okay, understood.
The same also for the Chicago as well.
Okay. Also a great presentation.
Thank you. Just the one general question. So
yeah,
graph approach. So what are the main, so what types of data can be used the graph approach DNN? Like, is any like geo information related data set can use this graph DNN method, or any
Yeah,
other
I think
requirement?
graph, especially graph, because GSNet was highly similar to graphical convolutional neural network, but they have added other LSTM as well. So it was quite possible to utilize graph-based within this, using these two data sets, because these two data sets, they are already the pre-processed information that we haven't done this pre-processing. This has been done already. So these two data sets makes it easier to benchmark for different techniques. So if you want like the correlation metrics or the similarity metrics, all this kind of stuff that you would require for graph-based approach, you could easily get using this when you are working on these two data sets. And I think as soon as you are conforming with this kind of representation, any geographical based data set for any task should be easier to be approached using graph-based solutions, graph-based learning.
Yeah, that's good. Thank you for your answer. I think in the future we might explore using this method in other like traffic flow prediction or other areas.
Yeah, this is a quite vibrant area of research. A lot of people are working on different tasks using different kind of similar techniques, but for different domain applications. So yeah, graph-based is quite interesting, and more, it has this aspect to it that's more interpretable in a way, but sometimes the scalability for them on different data sets or on a large data set might not be the best, especially given this kind of metrics. But if you don't care about this kind of performance or real time, yeah, it would be much, it could be, has this benefit of more interpretable results.
Yes. Thank you very much. Any other questions? So if no, I can stop the recording.